Okay, welcome to another video. This video is going to be talking about kinetic energy. This is our first energy bit, so we're going to talk energy that is neither created nor destroyed. All energy ever does is it passes from one form to another. In classical mechanics, we're going to be talking about energy moving from a kinetic form, from a moving form, to a potential energy, to stored up energy, such as being on top of a tall building. You've got a lot of potential energy. For our immediate purposes, and that of mechanical energy, we're going to go ahead and define energy as the ability to do work. So looking at the equations I've got set up here, kinetic energy, Ke, is going to equal 1/2 the mass of an object times the velocity of that object squared. Don't necessarily believe me on that formula. We're going to derive that in just a moment. And we're also going to derive the next set of equations, which would be work is simply the change in kinetic energy. That's 1/2 mv final squared minus 1/2 mv initial squared. Alright, so let's derive this from an equation you already know. You know the kinetic velocity formula. We have velocity, there we go, velocity final squared. It's got to equal the velocity initial squared plus 2 times the acceleration x final minus x initial. Well, first, what do we know? X final minus x initial. That's simply what we looked at yesterday. That's just d. Alright, so putting that all together, we've got v final squared equals v initial squared plus 2ad. Go ahead and solve this for a. Your a is going to equal your v final squared minus your v initial squared all over 2d. Now we solved that for a reason, and we'll get to it very quickly. So we're going to have to step back into yesterday, where we have our work net is going to equal the net force times the distance. Okay, so we can go ahead and break that force net down into mass times acceleration times our distance. Yep, that's where we're going to use the acceleration. So let's go ahead and plug this thing in. So our work net is going to equal mass times velocity final squared minus velocity initial squared all over 2 times our distance times our distance. Now, of course, we know, first off, we can kill those d's and to cancel out very nicely. So let's clean this up a little bit. We'll pull the 1/2 out. 1/2 m times v final squared minus v initial squared. So what we've just found is our work net has got to equal 1/2 mass of the velocity final squared minus 1/2 of the mass of the velocity initial squared. So what we have is the kinetic energy at any given point in time for an object simply equals 1/2 mv squared, the v squared at that time. The work done on an object equals the kinetic energy at the last moment in time you're looking at minus the initial moment in time you're looking at. So the kinetic energy final minus the kinetic energy initial. Now let's go ahead and put this in motion and look at a couple of problems that will hopefully make this make sense. So the first problem here, the first assignment, is a 145-gram baseball is thrown such that it acquires a speed of 25 meters per second. First question is, what is its kinetic energy? Second question is, what was the net work done on the ball to make it reach the speed if it started from rest? Well, the first question's pretty darn easy. Your kinetic energy is going to equal 1/2 mass velocity squared. So let's go ahead and just plug that in. So that's going to equal 1/2 times 0.145 kilograms. And remember, we need to use SI units, so we need to use the kilograms there, times our 25 meters per second squared. And what we end up with there, if we pull our nifty little calculator out, our kinetic energy is going to simply be 45 joules. Alright, so the second question was asking us, what is the net work done on the ball to make it reach this speed if it started from rest? So if it started from a velocity of 0. Now remember, our work is going to equal the change in kinetic energy. So that is the kinetic energy at the final moment in time minus the kinetic energy for the initial moment in time, which we just found the final. We know that's 45 joules, and we know that at the initial point in time the velocity is 0. So if our velocity here is 0, 1/2 m doesn't quite matter, it's still going to be 0, so minus 0 joules. So our work is going to equal simply 45 joules. Okay, so let's take a look at another problem. Second assignment. How much net work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? Well, it looks very akin to the last one. So our work is going to equal the kinetic energy final minus the kinetic energy initial. Remember, that's just 1/2 mass times the velocity final squared minus 1/2 mass velocity initial squared. Go ahead and plug that in. Whoa, hit the fast forward there on you. So I end up with 1/2 1,000 kilograms times our 30 meters per second squared minus 1/2 1,000 kilograms 20 meters per second squared. And that, if I plug it into my calculator, ends up being 2.5 times 10 to the 5th joules, or about 250,000 joules. Now let's try one more problem. It's virtually the same as this. Changing two numbers. We are going to be changing our 20 to 30 and our 30 to 40. Now I'm going to go ahead and ask you to pause the video and let you solve this one. I'll tell you what I got in a sec. Okay, so as you can see, I got the work to be 3.5 times 10 to the 5th joules. Now we changed the same amount. We changed 10 meters per second increase. Why in the world did it take so much extra energy to have another 10 meters per second increase? To put this in perspective for you, your 10 meters per second is approximately equal to 22 miles per hour. 20 meters per second, about 44. So we're going from, in the first problem, 44 to about 65. In the next problem, we're going about 65 to somewhere about 85, 90. So why does it take so much more energy? With that, I will leave you, and don't forget about the other problems that are on As You Learn. Thank you.